So in C++, we like to make rules, and then we like to wantonly break them. But some rules are so fundamental, we wouldn't dare break them at all. For example, you wouldn't move a stack frame. And so if you were writing asynchronous code in std execution, which has an operation state, which is the analog of a stack frame, you wouldn't move that either. And so if you came to my talk earlier today, you'll know that I avoided this by having all of these child operation states in a linked list so they wouldn't move around in memory. I initialized them like this. I had an immediately invoked lambda expression. I prepared a list. I looped over a range. I emplaced each and every state containing an operation state, which of course avoids moving them because of the reference stability requirements of list, and then I returned it. But C++ developers hate list, and they really love vector. So it would be really nice if we could do something like this, if we could put our immovable types in vector. But vector really likes to require move insertability, but maybe things have changed, so let's take a look at its constructors. We see one that gives us hope here. If we can construct a vector from a range, maybe it knows how much memory to allocate beforehand and won't try and move those objects, and we can actually achieve that. And so we go and look at the requirements of this constructor, and we see that precious second bullet. If the range models size range, we don't need move insertability. We can actually yield move-only types from our range. As an added bonus, list actually has a constructor like this too, so we can use some fancy generic programming to select vector when we want it and list when we want it. We can rewrite that code like this. We use conditional t on size range to select vector when it applies, and then we rewrite our initializer to use the from range constructor. We pass in a transform view, which is parameterized on our range, and in the lambda we pass the transform. We use C++17 guaranteed RVO to return our immovable type and synthesize it in place in the storage of our vector. But that wouldn't make much of a lightning talk because I'm nowhere near out of time. And so if you go to compile this, you end up with a compiler error like that. And we can blame everyone's favorite C++ standard library feature for that because, of course, this is allocators are to blame for this. And the reason for that is because allocators don't just get to allocate memory, they also get to determine how you construct elements in that memory, which means when I return that unmaterialized PR value, it needs to be materialized, to be bound to a reference, to be passed to this function, and of course, it's immovable, and so everything falls apart thereafter. We were so close to getting what we want with vector, and we were stymied at the last minute by allocators. But there's a whole C++ language out there for us to wantonly abuse. Maybe we can abuse implicit conversion in order to wire the synthesis of that PR value all the way through the allocator machinery, all the way to the final point where the element is actually constructed. And you don't need to go and implement this paper yourself. You can just use the implementation that I've contributed to Beeman. You can see me implementing it in Beeman right here, along with a bunch of other great people who either are at or were at this conference. And so now that we're armed with this, we can go back and we can revisit our example. Instead of trying to return a PR value directly, we return an elide that wraps lambda that returns the PR value. Elide passes through all the machinery, and then at the last possible moment, it implicitly converts to state underscore by invoking this lambda. But there's something curious on this slide. Why am I constraining this generic lambda? Why can't I just write auto ref? And I think the reason for that speaks for itself. Because no one wants to encounter this. No one wants to pick through what's on the screen. No one wants to find that the one load-bearing part is this const, because this is the compiler trying to figure out whether or not it can actually put the begin overload on transform view in the overload set. And to do that, it needs to figure out what my lambda type would return invoked with the value type thereof. But my lambda type returns auto, and so it needs to build the body, which doesn't build, which doesn't fail in a way that's Safini friendly, and so it just fails overall compilation, which is absolutely fantastic and is a completely usable feature of the language and did not waste a large amount of my time on the phone with Zach, thereby transitively wasting his time as well. But before I give you guys too much hope and you walk out going and doing this with your own vectors, I just want to warn you, don't try and do this with a sign range because reasons that are unclear both to me and the author of the paper that added it, it requires assignability for some reason. Maybe I'll write a paper.